Okay, so our goal by the end of this video is to be able to solve real life application problems dealing with normal distributions. So here we're going to actually see some actual real life examples where the normal distribution calculations can be used to, figure out, solutions. Now, when we're dealing with problems like this throughout the course, particularly if you're in AP statistics, it's very important that you show your work and are clear with what you're doing to the reader, because that's how you're going to be graded. If they can't follow along with what you're doing, they can't justify giving you a full score. So I would advise you to follow these 3 steps. Make sure you always state the distribution and what you're trying to figure out, and then have an area where you're doing the calculations, whether you're doing it mainly by hand or with a calculator. Just make sure you have some form of work being shown, and then make sure you always answer the question in context. The readers and teachers like myself, we don't want to just see students memorizing formulas and step-by-step methods to solve these problems. I have no idea what they're actually trying to figure out. We really want to make sure that you understand how the math behind the statistics connects with the real life, context of the problem. So always make sure that you make sense of your statistics answer in like a real life, way. Okay, so let's go through some examples because it's always the best way to learn this stuff. Okay, so here we have a scenario where, famous Rafael Nadal, tennis player, he averaged 150 miles per hour on his serves. And we're going to assume that his distribution of serves is normal and it has a standard deviation of 6 miles per hour. So based on this, what % of his serves would you expect to exceed 120 miles per hour? Okay, so first, let's write, what type of distribution we have, which is a normal distribution. So we can just write n of, and then let's define what our mean is. Our mean is told here to be 115. So we can write, 115, comma 6, because that's our standard deviation. Remember that for normal distributions, we use this notation n of mu, comma sigma. So this automatically tells you that the mean is 115 and standard deviation is 6. Okay, so what are we trying to find in terms of normal distribution? Well, let's draw a picture that represents this. So draw a sketch of a normal curve as best as we can. It's normal with a mean of 115, standard deviation of 6. So let's draw, I like to draw a line right through the middle and top to represent where the mean is. That's going to be 115. And we're trying to find what % exceed 120 miles per hour. So 120 is greater than 115. So we'll just say it's something like over here. And since we say exceed, we're trying to figure out this, area. Like what is this area in this distribution? That's our goal. So for that, we're going to standardize his value and then use the standard normal distribution to figure out the area to the right of the z-score that matches or corresponds with this value of 120. So, for example, what I like to do to give you a clear idea of what we're doing is we're still looking at normal distribution, but again, remember we're changing it or transforming it so that has a mean of 0 and a standard deviation of 1. So here again, that's the 0, and we want to find the z value here that has that same area as this. So for that, we're going to change our value of 120 into a z-score. And remember, let's recall our formula for z-score. Z is equal to x minus the mean over the standard deviation. So in this case, our x, our observation value, or the value we're trying to figure out is 120. Our mean is 115. Our standard deviation is 6. So we have about 5 over 6. I think it's 0.83. So 0.83 repeating. So this Z value would be 0.833 repeating. So essentially, our problem becomes, what's the area to the right of the Z score of 0.833 repeating? And then for that, it becomes simple. We just go to our normal table A. We, again, when we're looking, at this table that shows the area to the left, if we find the area to the left of Z, we can simply then subtract that from 1 to find the area to the right. So let's look at 0.83. So 0.83, 0.83 would give us about 0.7967. So an area of 0.7967 is to the left of this. So this area here is 0.7967 approximately. So that means this area would then be just 1 minus that 0.7967, which is going to be a little more than 0.2. About 0.2033. .2033. So then we can just say that about 20.3% of Nadal's serve would be expected to exceed 120 miles per hour. Would be expected to, whoa. Actually, a little funky. All right. Now let's look at this next one, which is building off of this problem. So based on this previous problem that we just did, what percent of his serves would be between 100 and 110 miles per hour? So again, let's draw a diagram to represent what we're trying to figure out. And our distribution is, again, normal with a mean of 115 and a standard deviation of 6. Let's draw that. Best we can. So normal with a mean of 115, standard deviation of 6. So if we're trying to figure out the percent of serves between 100 and 110, we're looking at, an area represented to the left of this. So we could say that's about 110, we'll say, and that's 100. We want to find this area. So we, again, are going to standardize this and look at the corresponding area between the corresponding Z scores. So we can draw, again, a normal distribution. Standard normal distribution, specifically where the mean is 0, standard deviation of 1. And we want to find these Z values. I like to, say we'll just call that one Z1 and call that one Z2. So first we just need to match them. We just need to match them up. We'll call this 100. We'll say that's our X1, and this will be X2. So we use again our Z formula, our Z-score formula. So let's find Z1 first. Z1 will be X1 minus the mean over the standard deviation. And Z2 will just be X2 minus the mean over the standard deviation. And we can just evaluate those. So Z1 will be 100 minus 115 over 6. And negative 15 over 6, which I believe is 2.5. And here we'll have 110 minus 115, which would be just the opposite of this 0.83, be negative 0.83 repeating. Okay, so that's, again, that'll be negative 2.5. This will be negative 0.83 approximately. And so now our problem simply becomes finding the area between negative 2.5 and negative 0.83 in terms of the Z-scores. So again, there's a couple different ways you can go about this. I like to find the area to the left of Z2, because that'll tell me, all of this. And from that, subtract the area to the left of Z1. And again, I like to call it like, I like to say, how do I push it? Z2 of, oops. I like Z2 of negative 0.833 minus Z1 of negative 0.25. And this isn't like a formal notation that's universal. I just like to use it to, kind of make sense. So this is saying area to the left of Z2, area to the left of Z1. That way we don't have to, subtract the values from one. We can go straight and find the areas to the left. So the area to the left of negative 0.83. Get our negative value, negative 0.83, and it'll be 0.2033. And from that, we subtract the area to the left of negative 2.5. So the area to the left of negative 2.5, we just go right here, 0.0062. We'll get about 0.1971. And if you picked up on this, being, the same area that's to the right of 0.83, because we know it's symmetrical, and that's good job, because then that's going to save you time down the road. So then our answer in context, we could say about 19.71% of the dolls served are between 100 and 110 miles per hour. Miles per hour.